Okay, so today's lesson is the final lesson on mains electricity, and we're going to focus today on how the electricity actually gets to our houses. So you know full well that the British countryside and most of the rest of the world is covered with overhead power lines. And the reason that we have to do this is because there aren't that many power stations. We made a decision a long time ago that if we were going to generate electricity, which is noisy and historically done using burning of fossil fuels like coal and oil and gas. So it's also very dirty and very industrial. You need a lot of deliveries of raw materials. We don't want that happening literally in our garden with our own personal power station. So we made the decision decades ago that we would consolidate our power into a handful of power stations dotted around the UK, and then we would take the electricity from those locations via overhead power lines to everybody's homes. We live at least 50 miles from the nearest power station, so we've got at least 50 miles worth of cable between us and our nearest power station. And today's lesson is about those cables. Okay, so the entire excuse me, the entire network of cables is known as the national grid. So let's have a little look at some aspects of it. So you've only seen them from the ground, a power cable, but you can probably appreciate by how far away and yet still how thick they look, that they are very thick, strong cables. We have made them out of aluminium mainly, because aluminium's a light metal, which means that we can hang it from pylons up in the air and the pylons will be able to hold the weight of it. And aluminium is also a very good conductor, which means that it's good for conducting the electricity for us. And we've made the cables as thick as we possibly can to allow as much electricity to run through them as we can. But ultimately, weight is against us. And if we were to make the cables any thicker, then the pylons would have to be closer together in order to hold up the weight. And we don't want to have pylons any closer together than we've already got them. There's already enough pylons taking up the skyline. So you can see the cross section there. It's a very chunky, well-manufactured object. We've done the best we can with the materials available to us, but ultimately this material still has some electrical resistance. Even the copper wires that we use in class have electrical resistance. It's just that we only use short meter lengths of it, so we never notice. But as I just told you, power stations can be tens of miles away from where people live, and tens of miles of cable, even a good conductor like aluminium, even a big thick cable, you know, as thick as your leg, even that still has resistance. And I remind you of this formula from last lesson, that the power dissipated by a resistor does depend on its resistance and also the current. Now, we have done the best we can to bring the resistance of the cable as low as possible. And now it's all down to the current. As soon as we start to push a current through the power cables, energy is going to be dissipated from the cable. The power cable is going to get hot, basically. You can see, therefore, that if we can't do anything about the resistance, we have to keep the current low. If we don't keep the current low, then what's going to happen is that we're going to send some electricity off down the power lines to deliver some energy to our homes. But by the time the electricity gets to our homes, all of the energy will have been dissipated in the power cable, warming up the environment. And there won't be any left by the time it reaches our homes. So we have to keep the current low. We have a device that does this for us. You see, it's not just as simple as turning the power station down. That's what happens in class. We turn the dial on the power pack down and the current goes down. But we still need the energy to get to our houses. And so we can't afford to reduce the overall power. That's the energy per second. People's microwaves and ovens and showers and heaters and lights, phone chargers, they're all using energy a certain number of joules every second. And across the country, that adds up to billions and billions of joules every single second. And the power station has to provide that. So the power output of the power station cannot change. If we want to, therefore, alter the current, we have to look at this formula and realize that the power needs to be kept the same. So if the current is going to go down, then we need to take the potential difference very, very high. The higher we take the potential difference, the lower the current will be. But crucially, the current times the potential difference will still equal the power output of the power station. We will still get the same number of joules per second delivered to our homes. It's just that it will be very, very, very high voltage, low current electricity that delivers that power for us. And when I say high voltage, I mean far higher than the 230 volts that we use in our homes. I'm talking hundreds of thousands of volts. So we have a device that is capable of doing this for us. It raises the potential difference, and as a consequence, the current goes down. We therefore send the low current through the power lines and then fix it again when it gets back to our houses so that it's not high voltage electricity coming into our houses. These devices that alter the potential difference and as a consequence the current are called electrical transformers. The type that takes the voltage up are called step-up transformers, and they're the ones that we attach to the power station. And when we do attach them to the power station, the current comes down very, very low, which means we can now send it across the network of cables in the national grid. The low current but high voltage electricity is very dangerous, which is why we have to put the power lines high up in the air. We could bury them under the ground, but there is always the worry that a tractor or a digger digging up the road will accidentally hit the power cable and electrocute the people who are digging. So we put the power cables up in the air to keep them away from people nice and safely. This diagram says 132,000 volts on it. It can be up above 400,000 volts. So these power cables really are seriously dangerous. And if you've ever wondered, could I climb that electricity pylon? Please don't. Electricity of that voltage can jump through the air and spark across a gap. And if you were to climb up one of those electricity pylons, you wouldn't even have to touch one of the cables. You would just get halfway up the pylon and it would jump through the air onto you. So please don't do anything stupid involving high voltage power lines. So we use a step-up transformer to make the current the voltage very high and the current very low. And then when we get back to our houses, we need a step-down transformer to reverse the process and bring the voltage back down to a safer, not safe, but safer level so that we can use it in our homes without exploding our devices. So that's the basic idea. What I'm going to do now is stop sharing this PowerPoint, and we're going to have a little look at a demo of it in practice. So if you can see what's in front of us here. Over here, I've got a 12-volt power supply. We're only going to use a couple of volts of it. And what that's going to be doing is playing the role of the power station. And then I've got somebody who lives right next door to the power station. So these red wires here, they're connected to the power station. And this bulb might be the bedroom light of you if you happen to live next door to a power station. So this is your bedroom light. And then also the power station is connected by these yellow wires to the high voltage power lines that are going to snake across the country. So you can just see these at the moment. Now, obviously, I can't show you 50 miles of power lines. So rather than use aluminium or copper, what I've done is use some resistance wire to just make a meter of it have a similar kind of effect by having lots of resistance. So this isn't aluminium or copper. This is just a different material to give us just a mock-up of the power lines. So there's going to be lots of resistance going on along this line and lots of heat dissipation as the electrons try to go through. And then at the other end of the power line, we're connected to somebody's house who lives a long way from the power line. So at the moment, there are no transformers in this setup, and let's just have a little look at how it works. I'm just going to gently turn up the power supply. So you can see this is a voltmeter that's connected to this bulb, and the bulb is just starting to glow. And there you can see we're at 2 volts, and this bulb is doing brilliantly well. Unfortunately, over at this end, in the person who lives a long way from the power station, they're only getting half a volt. And the reason they're only getting half a volt is because these power lines are sapping the energy out of the electrons before they get to the house. So there's 2 volts in total, only half a volt is making it to the bulb, the other 1.5 volts are being lost in this power line. These are 1.5 volt bulbs, so hopefully I won't break it, but I just want to take it high enough that the other bulb comes on at least a little bit so you can see it, right? So you can see this one's dazzlingly bright, this one's just about on. It really isn't fair on the people who live furthest from the power stations. They're just not getting much power. Their toaster will toast slowly, their kettle will boil slowly, the water that is heated by their heaters will heat slowly, and their power showers will always be lukewarm. Their lighting will be dim. So we need to fix this, otherwise the whole idea of putting power stations a long way from houses isn't going to work. I'm going to turn this back down. And what we're going to do now is just rewire it a little bit to include some transformers. Okay, so let me show you what a transformer looks like. So what this is some cable that has been wrapped round and round and round and round and round, just a hole. Let me just take it apart a second so you can see it. So it's just a hole in the middle, and we've just wrapped some wire round and round and round and round and round it, and then we've just taped it up with some bandage and kind of varnished it to make sure it doesn't fall apart. And then we've got 2 of the things, and we're just going to connect them together by a lump of iron, which is just going to kind of clamp around them. You can see the iron there, just to hold it in place so that I don't have to stand here and hold it. Just got a little clip that's just going to hold those bits of iron together. Now, I'm deliberately rushing through the construction of a transformer because they are magnetic devices, actually, and we are going to be doing a topic all about magnetism at the start of year 11. And so we're going to come back to this and really have a good look at how transformers work then, and maybe you'll get a chance to make some yourself. Okay, so what I'm just going to do is this transformer is going to sit between the power station and the power lines. So what I'm going to do is, I'm just going to turn this off, you'll see why in a minute. I'm going to pull the wires out of there. So these are the 2 coming from the power station, and they're going to go into the transformer first, and then they're going to come out of the transformer and come up into the power lines. So just plug those in. Okay, so we've got our step-up transformer now. And the reason it's a step-up transformer, by the way, if you can just see, I don't know how well that's showing up on the camera. Let me bring it down. On the front of this, it tells you how many times the wire has been wrapped around. So for a step-up transformer, we're going to wrap the wire around a small number of times on the power station coil, but we're going to wrap it around a lot of times on the power line coil. So this one's been wrapped around 60 times. This one's been wrapped 1,200 times. So we've got a factor of 20 difference going on there. Remember that, factor of 20. Okay, so we're stepping it up. So hopefully in the power lines now, we've got high voltage, low current electricity, but that wouldn't be safe to bring into our homes. So we're going to need a second transformer now to step it back down again. So again, we'll take it out of the power lines, and before we send it to somebody's home, we'll stick it into the transformer. There we go. Okay, so the electricity's now stepped up, high voltage, low current, and it comes back down, step down again by the same factor of 20, back into the person's home, and hopefully nice and safe. And there's one more thing that I just need to do before I turn it on. Whenever we've used the power supplies, we've always plugged it into these red and black terminals. And these red and black terminals, as you know, are the normal, regular battery-style power supply, and it produces direct current. What I just need to do before I turn it on, because it's a bit dangerous to use direct current, I need to use alternating current. Now, all I'm going to say for now is that transformers only work using alternating current. They don't work for direct current. So in order to make this work, we have to use alternating current. So let's do the same all over again. So if I bring this up now, oh, hang on, sorry, I did forget one thing. I just need to change my voltmeter from DC to AC. Okay, here we go. So you can see that the power's coming up, and already you can see that both bulbs are on and both bulbs are bright. Now, if I just bring that down just to 2 volts kind of exactly-ish. So you can see this one's on 2 volts, and this one is on kind of 1 1/4. So it's not perfect. It's not like I haven't lost any of the energy, but I have kept far more than I had before. It's not quite at 2. If I make these things even better, there are manufacturing ways. I mean, I've just thrown it together in front of you on the camera. So if you manufacture them better, you can make them very, very close to 100% efficient. But obviously these on the desk in front of you aren't quite managing that, but they're managing it well enough that you can see that both bulbs are on and both bulbs are bright. I'm just going to turn this off just for 1 second so that I electrocute myself. I'm sure that would be funny for you on camera, especially while I record it. I'm just going to attach a voltmeter to these cables just so that you can see the effect. So if I just nudge that around just a little bit. So you can see that the 2 volts there is being stepped up by about a factor of 20, up to about 40 or so volts, which is just your indication that I'm not playing a trick on you or anything. It really is 40 volts instead of 2 volts that's coming through these power lines. Just going to turn that off again before I do a comedy accidental touch. 40 volts is around about the power, the potential difference of a cattle fence. And if you've ever touched a cattle fence, you'll know that it doesn't do any nesting damage, but it's not very pleasant. Okay, so that is the simulation, just to show it you in action. We're just inserting a step-up transformer between the power station and the wires, and then a step-down transformer between the wires and the houses. And whatever is going on with the wires happens to the electricity. So here we've got the number of wires on one coil is 20 times bigger than the other coil. So the volts went up by a factor of 20 and the current went down by a factor of 20. And likewise over here, we've got it the other way around. So again, the volts come down by a factor of 20 and the current goes up by a factor Okay, let me return to the PowerPoint. Okay, so that was a demonstration of this diagram. And towards the end of this lesson, when I finish talking, it's this diagram that you're going to need to pop into your book. Okay, the step-up transformers are next door to the power stations, so you're not likely to find one of those unless you go visit a power station. But the step-down transformers are wherever there are houses, and you live in a house, so there'll be one near you somewhere. So they often look a little bit like this, kind of metal fencing with spiky tops and a big sign that says danger of death, keep out. And inside there's kind of like something that's usually been spray painted, a kind of gray color. Sometimes they're in brick buildings to really keep you out. What I would say is please pay attention to that sign. If your frisbee goes inside the fence, just get a new frisbee. If your ball goes inside the fence, get a new ball. If your dog goes inside the fence, get a new dog. You risk painful, horrible death by going inside that building. Those machines carry hundreds of thousands of volts. They will kill you instantly. Please pay attention to the signage and stay out of those areas. Okay, yeah, see if you can find the one near your house. There'll be one probably on your road somewhere. There are two either side of the school. So next time you're walking to school, it's one by the rugby club and one the other way down Priory Lane on the other side of the road. Okay, and this is just to underline what I said. We will come back and we will study transformers and we will look at how they're constructed and how they work when we learn some more about magnets. But just fix in your mind now, they only work with alternating current, which is the reason why we have continued to design power stations that produce alternating current, because we need the transformers. However, in the future, should it be the case where every home has got solar panels and a wind turbine on top, and we don't need the transformers anymore, who knows? Maybe we'll switch to DC instead. Okay, that was 20 minutes, which obviously means that we're not even halfway through the lesson left. So what do I want you to do? I want you to pull up this PowerPoint from Google Classroom, please, and I want you to make notes on that slide. I want you to draw the picture with the labels and make sure that you understand the function of the transformer in, one more time, keeping the current low so that we do not have any power dissipated from the power lines. We want to keep all the power for the homes. So keeping the current low means that as it passes through the resistance of the power lines, it doesn't lose any power. Oh, by the way, people often ask, I forgot to say, birds can sit on the power lines, okay, because the electricity needs to be able to flow through them to somewhere else. So when a bird sits on a single power line, it's not going to get electrocuted because there's nowhere for the electricity to flow to. However, if you had some freakishly long-legged stork that tried to straddle the lines and put a foot on each line, then yeah, that would be a dead bird. Okay, once you've made your notes, over the last few lessons, we have been working our way through chapter 5 of the online textbook. And I've been asking you to chip away at the questions from each of the double-page spreads. I'm sure there will be many of you that have finished all those questions, but this is an opportunity to do so if you haven't done so yet. I also mentioned that next lesson will be a consolidation lesson as well, and we'll get the end of chapter questions done then.